Hello everyone, this is 5/5 Calculus, and in this video I'm going to be going over optimization. Well, as far as I'm concerned, I know that every calculus course really does touch upon optimization because it's that important of a topic. Whether you're in regular calculus, advanced calculus, vector calculus, you're going to touch upon optimization. And that makes sense because it has a lot of real-world explanations and context. For example, in this depicted graph, it could be the average total cost of a firm. And basically what that is like the cost that a firm must pay in order to produce a certain output of quantity and production. And so it might be useful for them to find out, okay, where can I operate at the minimum ATC? In other words, where can I operate at the minimum level of cost while also getting the most out of my production? Well, as you know, optimization can help with that. And that is because if I draw some tangent lines of this ATC curve, which I labeled f of x, you can see that it truly hits 0 at one point, representing a minimum. Let's say that's the horizontal tangent line, in which the slope is simply dy over dx, and that is equal to 0. Well, it is useful to find where f prime equals 0 in order to see whether or not the original function, which represents the model that we're trying to optimize, is a max or a min at that point. And so now I'm going to describe the general process. So usually you might be given f of x and be asked to optimize this function in terms of one variable. Also, you may be given a constraint that involves two variables, but you can easily isolate one of them. For example, it might be perimeter. So perimeter is usually equal to 2 times the length plus 2 times the width. And the perimeter is going to be a constant value, let's say 48. And so you can very easily isolate for one of them. Let's say we're doing width. So the function with width would be, well, it's going to be 48 minus 2L, okay, and then divided by 2. So it's going to be 24 minus L. And we can very easily find the derivative of that, and then find which width is going to give us the optimal area. Also, one thing I forgot to mention is that with constraint, you need to find another equation. In this case, it would be the area of the figure. You need to find another equation that actually relates what you're trying to optimize. And so let's delve into this general process more clearly. So let's say you're given f of x. You must find f prime of x such that it equals 0 for the reasons described above. And that will basically give your endpoints. Also, it is important to mention that the problem may also state a domain, but in the cases that it doesn't, you'll have to find a feasible domain, which is basically the simplest domain which makes sense in context of the problem. Okay, so let's say that this is a very general process that I'm sort of trying to explain. So let's say the domain is simply, or not simply, this is actually the most complex, but it's negative infinity to infinity. Well, in that case, you will have to find where f prime of x equals 0, and that gives you your critical points, which I'll abbreviate as CPs. Well, there are always at least two candidates for your CP, because they are the endpoints. Any point on the domain in which f prime equals 0 is another candidate to your CP. So let's say for this general example, f prime of x equals 0 at x equals b. Let's actually say plus minus b. That'll make it more interesting. That means there's a square involved. So as CP, there's two domain values at which f prime of x equals 0. So that means our available candidates are going to be negative infinity, and obviously x can never equal that, it can only approach, in which we use our limit knowledge. Let's go in order, negative b to positive infinity. Well, what we simply do is plug these back in to original f of x. And so what we have is limit as x approaches negative infinity of f of x. Let's say it yields one value called a1. And then we don't need the limit because we can actually plug in b, given that it's defined. Alright, actually I was talking about negative b. Let's say that gives a2. You could do this for all the critical points. a3. And actually we do have to take the limit for infinity. And in this domain we would have to observe n behavior, which is with these limits. Let's say it gives a4. Well, we would have to compare a1, a2, a3, and a4. Given whatever the problem wants, whether it wants the biggest or the smallest, we would select which one of these candidates fulfills the requirement of the question. So let's say a2 completes that. Well then, our optimal point is that f of negative b equals a2. And so that's the general process. Okay, now that we've got that established, let me move on to a very bread and butter example. I know if you've already touched upon this topic in your courses, you will know this example. So let's say your house, you want a backyard. That's not a straight line. Apologies. So let's say you want a backyard, and one side of the fence of your backyard is bounded by the wall of your house. So there are only going to be 3 side lengths. And let's say you only buy enough fence. Let me actually do that in a different color. This is the pink is your fence. Let's say you buy a fence, like a certain quantity of fence. Let's call it, let me think. Let's say you buy 100 meters of fence. And you have to constitute that over 3 sides. Because, well, one of the sides is bounded by your house. You don't need to buy fence for that. Okay, so using our knowledge of geometry, this is a rectangle, right? Also, your garden is this shaded green. We want to find what gives you the most garden. What combination of side lengths of the fence, given our constraint of 100 meters of it, gives you the most amount of garden. In other words, how can we optimize the area of this rectangle, knowing that the side lengths must add up to a certain aspect? Well, let's set it up mathematically. So, using our knowledge of geometry, these etched lines really represent congruence. So, if we call this side length, I don't know, S, this has to be S as well. And something really quirky variable, I guess, will be Q. Alright, so we know that 2S plus Q must equal 100. Well, what do we also know about the area function? Well, it's just S times Q. Now, we have 2 variables and 2 unknowns. An important thing to remember about math is that the amount of variables you have should always equal the amount of configurations you have. configurations as in the amount of equations in your system. And so since we have S and Q, those are two variables, we also have two equations. One is the constraint, which is the 100 meters of fence, and one is the area. And so remember that the area is going to be in meters squared, and this is in meters because I said 100 meters of fence. So now we really just have to isolate for one of the variables. And I guess Q looks the easiest, so I'll just do that. So 2s, this is from the perimeter equation. 2s equals 100. We have Q equals 100 minus 2s. So now what you do is go back to the area equation is equal to S times Q, but we have another expression for Q. So we can write area solely in terms of S. It's equal to S times 100 minus 2S. Now let's distribute. It's equal to 100S minus 2S squared. Now this, ladies and gentlemen, is the function that we are trying to optimize. How do we do that? Well, let's follow the general process. We find the critical points, and we basically evaluate which one gives us the highest area. Okay, so now let's introduce our feasible domain. We need a different color for domain. Domain of X, well, okay. Let's think here. Let me use set builder notation as well. Let's look at the picture. Let's say I already bought 100 meters of fence. Now I have to construct two walls that are congruent and one wall that connects them. Okay, well, since I'm building walls, they have to be more than 0. If they're 0.1 meters, sure. I don't think I'm going to use all the fence, but that's definitely a part of our feasible domain. So let me actually get rid of this bracket. Let me use this one. So it has to be a little bit more than 0. Right. And it could realistically be 100. I could spend all the fence on one side if I wanted to. If I decided that would give me bounded area. It has to be a little less than 100, keep in mind though. So there will be other sides. But I can use 99.999% of the fence for one side length if I so desired. If I think that's going to get me near the critical point. So let's actually find the other candidates. We have our definite two candidates, which are 0 and 100. So let me write, this is the function that we got. A of s is equal to 100s minus 2s squared. Well, you find the derivative of that, and where it's equal to 0, it's just simply that, minus 4s. A prime of s equals 0. Sorry about that, not equals 10. Equals 0. Okay. 100 minus 4s equals 0. You get that 4s equals 100. Therefore, s equals 25. Okay, that's our only critical point. So now we got our candidates. CPS, not clicks per second. Critical points. We got 0, 25, and 100. Remember, I would take the limits of these, but since we know that these are going to give you back to 0, so basically a of 0 is going to get you 0. A of 100 is also going to get you 0. Why is that? Well, because, let's go back to our equation. Yeah. So if s equals 0, then s times q is going to be 0. And if s equals 100, well then q is going to be 0. So the area is still 0. Well, what if s equals 25? So a of 25. So these are going to be 0. That's obviously not optimized. So we have to pick this one. Well, first, let's find what it is. Let's use this equation right here. So we have a of s is equal to 100s minus 2s squared. Now let's find a of s such that s equals 25, and that's just simply equal to a of 25. Therefore, it's going to be 100 times 25 minus 2 times 25 squared. Let's try to do this. 2500, yeah, minus 2 times 25 squared is basically 5 to the 4th, which is basically 625. And 2 times that is going to be 2500 minus, let's see, 1250 is that? Oh my goodness, we got 1250. That's non-zero. And that is surely, ladies and gentlemen, our optimal area. Well, I hope you enjoyed this video where I went over the general process of optimization along with one of the most common problem types that you're going to come across. Stay tuned and be sure to look out for my 2 next videos, which are also going to be related to optimization, but they're definitely going to be more advanced examples, and definitely ones to look out for your exams, right? Calculus teachers love to test students, love to test their limits. Hey, and be sure to stay tuned in order to know how to do those problem types. See ya. Thank you for watching.